All right, we are back. We are back. Sorry, we're actually back. Are we? My phone died. Are we back? We're probably back. Hold on, my phone is actually dying. I can't read chat. Yeah, I'm reading chat from my phone, so one sec. There we go. All right, we're back. We're back. Yay. Okay, let me test the. Let me test chat. Hello, Frost. Welcome to the stream. I had to restream there. I had to restart my stream there because I accidentally messed. I fucked around and I found out. We're so back. Yup. Okay. Perfect. Chat is not working again. Wait. Chat overlay is not working again. Wait. Whoop. Come on. Chat overlay. I summon you. Please appear. Excuse me. Chat overlay. Hello. Chat overlay is not working. I'm so cooked. Okay, is it functional now? Is the chat overlay functional? Can you play Silk Song on stream? I don't think the computer can handle that. I'm gonna relog into Streamlabs, so the chat overlay should show. Oh wait, it's up. Okay. I generally don't know what happened. I don't know how it came back up, but not going to complain. All right. Well, apologies for a little. That was a little rough, but it's all right. Everything's okay now. Everything's okay now. Right. Okay. So, back to where we were. Next up, we have to take the derivative of the Lagrangian with respect to x. In our case, it becomes straight up just mg, and it's equal to 0. So now we just take the derivative, and so we have 3 over 2 m x double dot, because we take the time derivative and mass is constant, 3 over 2 is constant, so the only one we have to affect is x dot. This becomes minus mg equals 0, and therefore x double dot equals to 2 over 3 g. And that is correct. That corresponds, that lines up with the question, and so this gives our answer. Yay! First question done. See, it wasn't too bad. Was it? When math more letter than numbers. It has always have this. Actually, let's see. 1, 2, 3, 4, 5, 6. That's 6 numbers here. You can see that there's 1, 2, 3, 4. There are only 4 letters in this term. Come on. Okay, maybe there's 5 over here, but there's a total of 6 numbers here compared to 5. Your argument is invalid. Don't talk about this one. This one is entirely. But let's see. There's more numbers here. Also, this isn't math, technically, this is physics. Alright, on to the next page. Anyone got any question with the previous question? With the previous problem we just finished? I'll continue on the next one. Well, if you want to type out the question, I'll go back to it. I'll get the next one. Yeah, math. It's physics more than math, but you know. Alright, let's see. Alright, the center of long frictionless rod is pivoted at the origin, and the rod is forced to rotate on a horizontal plane with constant angular velocity omega. Alright, so first of all, let's continue. Perfect. So first of all, I'm gonna write out, if I can write a straight line. Oop. And we have a metal rod. I'm gonna use a color gray for this one. And we have a metal rod that goes like this. We could draw it well enough. Like, you can think of this thing as a table, and then the metal rod is on the table, and then it's spinning around. I don't think the length of the rod matters for this question. I already skimmed through this question like a little bit before I started streaming. So the object here of mass m, I'm guessing, is it mass m? It doesn't specify the mass. Actually, yes, it does specify mass. The mass is m, and obviously the whole rod is rotating at the angular velocity omega. Okay. So the center and is forced to rotate on a horizontal plane using r as your generalized coordinate, where r and phi are a polar coordinate on the bead. Let's solve Lagrange equations for r as a function of time. And what happens if the bead is initially at rest at the origin? If it's released from any point, it eventually grows exponentially, and explain the results in terms of the centrifugal force. Okay. So with that figure that we have drawn, let's write out the Lagrangian. Again, the Lagrangian here. Hold on. On one hand, I want to talk about the constraining force. I'm going to talk about the constraint force. It's going to take a little longer, and it might be a little confusing. You know what? I'm going to solve it normally first, and I'm going to solve it with the constraining force approach. Alright, so first of all, let's find the Lagrangian. The Lagrangian is, again, in our case, t minus v. Yeah. And obviously t here is the kinetic energy. It's going to be equal to 1/2 mv squared. So if this little object here is in motion in the polar coordinate, it's going to have the radius r as 1 degree of freedom. And it's going to have the theta as the other degree of freedom. However, the theta is also constrained by the rod itself. So we know that ultimately the velocity of the object is going to have, like, for example, over here and in polar coordinates, right? In polar coordinates, the velocity is going to comprise of two parts. That is the radial part. Which is r dot in the r direction, and the tangential part. And the tangential part is r times theta dot, or, well, alternatively r omega in the tangential direction. And therefore, the square of the velocity, the speed squared is going to be equal to r dot squared plus r omega squared, as per the Pythagorean theorem, which we just happen to need v squared over here, so we can just straight up write it in. So we have mv squared, in this case is going to be r dot squared plus r squared omega squared, and that's our kinetic energy term. And then the next up we have the potential energy term. In our case, there is no potential energy. There's no force that's directly acting on it apart from the constraining force that is spinning the rod around, and the force that the rod itself is actually acting on the object, which is not really how do I explain it? It doesn't do work. Wait, does it? Because it is a constraining force. In this case, you don't really express it in terms of potential energy. So I wouldn't write it in terms of potential energy, if that makes sense at all. So what I'm simply saying is that the Lagrangian here, what I'm saying is V equals 0. There's no potential energy term in this case. So ultimately, the Lagrangian is just gonna be 1/2 mr dot squared plus 1/2 mr squared omega squared. And of course, we next plug it into the Euler-Lagrange equation. We use r as our coordinate here, and we take the time derivative. See, this is how easy Lagrangian mechanics is. You just write out the kinetic energy term, and then you take the derivative as you need, and you get the equation of motion. It's that easy. Sometimes it is a little complicated, but like most of the time, it is kind of just way easier than Newtonian mechanics. They should teach this in high school for real. We take that time derivative, we're gonna get mr omega squared, and it's gonna be equal to mr double dot minus mr omega squared, which is equal to 0. And therefore, we can conclude that r double dot is equal to r omega squared. This guy is constant, so we just have r over here. And this is and this is our equation of motion, how r changes over time. This tells us how r changes over time, and this actually is a fairly simple equation that we can solve easily. So we assume r double dot, I'm just going to write this, minus r omega squared equals 0. To solve this, we assume that r equals to e to the power of lambda t. Why? Well, the reason that we are assuming r equals e to lambda t is because we just assume so. It's like the easiest. E to lambda t is a simple answer. It's a simple answer, and if you take the derivative, you get the same thing. You get r back multiplied by lambda. So you take the derivative twice, you also get lambda squared, and you also get r back. And because the right hand side has to be 0, it means that the r here and the time derivative of r has to cancel out for all input t. And so we can conclude that r double dot here and r here, these two must have a similar form. And that similar form, of course, is the exponential function. So if you take the time derivative of r here, it'll make sense. It will make sense. If we take the time derivative, we get r double dot is equal to lambda squared e to lambda t. And therefore, this boils down to lambda squared minus omega squared e to lambda t equals 0. Okay. Now e to lambda t just becomes 0 because, yeah, Lagrangian mechanics looks fun compared to the sheer hellhole I have to go through while solving it with Newtonian. Yeah, you have to like write out all of those free body diagram, and then just you have to like make sure you write out every single force. This one is never 0, so you can bring it over to this side and then divide it by this guy. So it becomes lambda squared equals to omega squared. Lambda equals to plus or minus omega. Yeah, it's Lagrangian mechanics. It's much better. Now that I see this, it's a little odd. I can't really say that it grows exponentially, can I? Alright, whatever. And therefore, r as a function of time, is equal to some initial r multiplied by e to the power of lambda. Well, in our case, it's going to be omega t. And that's how we can conclude that it is in fact growing exponentially, because the r here is being accelerated by the centrifugal force, the pseudo force, that is the centrifugal force, and it's going to look like the object is going further and further away from the center. I think I did that right. To be more general, though, to make sure as the most general as general as possible, I'm gonna write this. Negative omega t. Yeah, because if you take this form and take the derivative, you'll realize that it will satisfy this equation. So r does in fact increase exponentially. As time goes on, this term goes to 0. As time goes to infinity, this term goes to 0, whereas this term goes to infinity as t goes to infinity. Therefore, we can conclude that this whole equation just becomes an exponential growth, gets close to an exponential growth. Yeah, show that r over time eventually grows exponentially. Eventually grows exponentially means it initially might not grow exponentially, but like as time goes on, this term gets very, very small. This b term gets very, very small because it's e to the negative exponent. It's e to the negative omega t. So like as t goes on, this term just decays exponentially, whereas this term grows exponentially. And because this term is very small, you can neglect it, and so r just basically grows in an exponential fashion. And that is the solution to this. Explain your result in terms of centrifugal force. Well, I'm just saying that the centrifugal force is directly proportional to r. Is directly proportional to r. Therefore, r grows exponentially. Simple. Yeah. But like the key point here is just this, though. And additionally, if r starts off at 0, and if initially it starts at rest, if initially it starts without moving r, and r starts off at 0, if it starts off at 0, it means that this whole term becomes 0. Therefore, there's no acceleration. Initially, it has no speed and it has no acceleration. Therefore, it's going to stay still at all times. So, if r equals 0, what happens if the beat is initially at rest at the origin? It's going to stay at the origin forever. Intuitively, it makes sense. If you put the beat right over here and it spins, it just spins around the beat. It doesn't really do anything, right? And that is this. And that is the solution to this question. Now, here's another new thing that I actually didn't know before this class. Before I took this class, because I already knew. What is it? I already knew the Lagrangian mechanics from before this. I already knew how to do Lagrangian mechanics, but I never knew this new detail that you can use Lagrangian mechanics to find force. How many problems in today's stream? 2. It's just this one and this one. But I'm going to explore another solution to this problem before we end the stream today. This stream is I normally stream all my homework, and normally I don't really get that much homework as practice problems. So that's that. Yeah. I normally get only like 2 to 3 problems each day, unless I like procrastinate a lot and then I stream all of them at once. In that case, I might get to like might have a little lengthy stream. Okay, so here's another way to solve the problem. Right now, what we have here is the fact that phi is not independent. Phi is constrained. And what we did was we applied the constraint that phi equals to omega t. Before this, we applied the constraint that and phi dot equals to omega. That is what we did before this. But what if instead of applying this, well, okay, hold on. Lagrangian equals to t minus v. So it's going to be equal to 1/2 mv squared, which is going to be mr squared plus 1/2 mr squared phi dot squared. And v is 0 again. So what we did prior was we found the Lagrangian here, and then we plug in the constraints immediately, and then we solved these equations. But what if instead we apply the constraint afterwards? Let's look at what happens if we apply the constraint after solving the equation. Obviously, you know when I place bet if it's going to be wrong or right. Okay, of course it's going to be wrong, right? Of course it's going to be wrong. If we take the derivative of that, we're going to end up with mr double dot subtracted by mr squared, no, mr theta dot squared. Sorry. And is equal to 0, and then we plug in the equation. Then we plug in the constraint, which is going to give us the same thing as we got before. Hold on. It's going to give us the same. It's going to give us the same thing as we got before, which is r double dot equals r omega squared. This is our first equation, which stayed true. It is still true. But what isn't true is the next equation, because again, now that we haven't put in the constraining, we didn't put in the constraint first. So what we have right now is we don't have the constraint. We have the no. When we have one constraint, which is this one, and then you take the time derivative, you get another constraint. But this is like the main constraint. If we have this, if we have one constraint in a system with 2 degrees of freedom, the constraint is going to reduce the degree of freedom down to 1. Each constraint reduces the degree of freedom by 1. So in our case here, we initially have 2 degrees of freedom, that is r and phi. Then we know that the bead is being spun around by the rod. Sorry. The bead is being spun around by the rod, which constrains the angle phi over here, and therefore we are left with just 1 degree of freedom, that is r. But if we hadn't applied the constraint and we used the Lagrangian right away, and then we apply the constraint later, what we're going to end up with is we take the time derivative of L with respect to phi dot subtracted by L with respect to phi. We're going to have d by dt of mr squared phi dot is equal to 0. Hold on. Is equal to 0. That is to say that this whole term is constant. Okay, is it really constant though? Let's try that. If we pull out the m and phi dot here, now we reapply the constraint. Before this, we didn't apply the constraint yet. Now we do it afterwards, after plugging it into the equation. What we have is we're gonna have d by dt of r squared omega equals 0, and then we pull out the omega, and then omega here is constant with respect to time. M is constant with respect to time. So we're gonna end up seeing the fact that d by dt of r squared is equal to 0, which is clearly false. Because this means that r is constant in time. So this is definitely not true. Something's off right there. So the main takeaway is that when you do Lagrangian mechanics, right, you must identify all the constraints first. When you do Lagrangian mechanics, you must identify all the constraints first and then apply it to the original Lagrangian. And then you use the Euler-Lagrange equation, as opposed to doing the Euler-Lagrange equation first and then plugging in the constraint later on. They're gonna yield different results. Okay? But we can also do one more thing, one new thing. That is to add in the constraint into the Lagrangian itself. We could add in the constraint to the Lagrangian itself, and we're going to be able to find the constraining force. Let me explain. I don't really know how it came to be. This is what I learned in class earlier today, and I feel like this is like an entirely new idea to me. I find it really interesting. So the Lagrangian originally is just t minus v, right? What you do is t minus v here without the constraint, without applying the constraint, and then we add in the constraint. I'm gonna write it as lambda f like this, where the constraint is written as f something equals 0. So I don't know if that makes sense. So I'm gonna just explain it. So the constraint here, we know that the constraint is phi equals to omega t. How can we write it in this form? Well, we can write it in this form by just saying that it's phi minus omega t equals 0. We can write it like this. Simple enough, right? So, because this is 0, this is the constraint over here is 0, that means we plug it into the Lagrangian, it shouldn't change the Lagrangian itself at all. It shouldn't be changing the Lagrangian because, you know, f must be 0 at all times. Therefore, we can now write this as 1/2 mr dot squared plus 1/2 mr squared phi dot squared plus lambda phi minus omega t. Again, this term is going to be 0 if we apply the constraint. If we didn't apply the constraint, this will be our constraint. This will be the term that will apply our constraint for us. Okay. The whole point that I'm trying to what I'm trying to say is when we have multiple degrees of freedom and we want to reduce and we want to apply constraints, we could either A, apply the constraint to the Lagrangian itself like this, like we did before. So like we plug in all the constraints first right away, or we add the constraining term lambda f here into the equation. Lambda, what is lambda? We don't know just yet, but it will make sense soon. But basically, we plug in lambda times the constraint, the holonomic constraint. Okay, if you can write the constraint like this is called a holonomic constraint. And from F here, we can plug it into the Lagrangian, and this is going to give us the constraining. This will give us the constraining force. I'll show you what it means. We take L, again, if we take the time derivative of L and then apply the constraint later on, let's see what happens. So first we deal with the... I'm not going to do the R coordinate anymore because we've done that like several times. We've done that twice. It doesn't change anything. So I'm going to do the phi coordinate right away. I hope what I'm saying doesn't make me sound like a madman. I hope this makes sense. I hope it's making sense. If it does make sense, just say something. All right, I'm gonna try and explain it to the best of my ability. I'm in college and it's 12 a.m. right now. What are you doing? I might go to sleep soon. Oh, you're in. Also, hello, welcome to the stream. Welcome back. Sorry, I haven't streamed in a while. But yeah, if we do that, we're gonna have d by dt, and we're gonna get mr squared phi dot subtracted by. Now, if we take this derivative here, what we're gonna end up with is just lambda. I think that makes sense. Because we take the derivative with respect to phi, this term is half phi. Oh, that's fine. I've been pretty busy too. I almost forgot about this. Yeah. I've been having a midterm exam, so I haven't been streaming much. The midterm exam was kind of easy though. I'm not quite sure I can say the same for the finals, but yeah. This term becomes just lambda because we take the time we take the derivative with respect to phi, partial with respect to phi. And so this is equal to, well, really this is equal to like, so like this is the angular momentum, L. Okay. This is the angular momentum L. This term is the angular momentum L. And this is minus lambda. Well, it's 9:33 here. Damn. We have quite a varying time zones here. Normally I stream like a little earlier than this, but today my brother has been playing Silk Song on my computer, so I had to wait for him to be satisfied. So I streamed a little later today. Anyway, this is the L by dt, the rate of change of the angular momentum, which means that lambda here is equal to the rate of change of the angular momentum, i.e., this guy is the torque. This guy is the torque that is applied on the object as it spins. This is the torque that is applied to the object as it spins. So you know now it's going to have the angular momentum changing over time, and this torque is the one that's changing the momentum. So what I'm saying is this term, this lambda term right here, is the constraining force. This lambda here is the constraining force. It is the force that is acting on the object that makes it that applies the constraint that we have written out. Back up here, of course, when the rod is spinning around, the force that it applied to the bead is going to be the force that the rod is spinning the bead around with it, along with it. And that force is a torque that we just found. Isn't that cool? I think that's cool. Well, the whole point is that when you have a Lagrangian, you can write out the normal Lagrangian without applying a constraint, and then add in the constraining term to it, and then apply it to the Euler-Lagrange equation, and then we have the same result, but we also have the constraining force added to it. I feel like it's really neat. You know what? How long have I been streaming? You know what? I think I can actually do one more problem. I kind of want to talk more about the constraint force anyway. So let me find a problem with a constraining force real quick. I kind of want a shorter problem, so let me scroll around. Lagrangian multiply constraint force, there it is, okay. Let me check. Okay, sure, let's do this one. This one seems fairly simple. I'm not going to go into much detail though, but I just want to give more example with the constraint force I was yapping about. Okay, so I'm sorry, Southern Heaven, I may have lied about the fact that there's only 2 problems. Turns out there's 3. You guys get a bonus. Okay. So, mass m rests on a frictionless horizontal table. Attached to it is a string which runs horizontally toward the edge where it passes over a small frictionless I'm just going to draw it out for you. Just going to draw the system. It's a classic system. Everyone knows everyone knows this. It's just this frictionless mass. It's just m1, and then we have m2 down over here. If I could, draw a straight line. Hey, that's nice. That's not bad. And we have m2. Okay. And write down the 2 modified Lagrange equations and solve them. So of course, on one hand, this really, this problem really has 1 degree of freedom. It's just how far. It really has 1 degree of freedom because we have this length over here, and then if we know this length over here, let's call it x, right? Is x? Yeah. If we call this guy x, we immediately know y because this one is going to be L minus x equals to y. But in case we don't know that, in case we we do know that, but like in case we don't want to apply the Lagrangian to the. We don't want to apply the constraint to the Lagrangian right away. We want to add in the constraining term, like we just did earlier. So let's do that. First of all, the constraint equation is okay. I'm gonna first write this. This is x and this is y. The constraining equation, first of all, is going to be f x y is equal to x plus y minus L. L is the total length of the rope. So x plus y, if x increases, y must decrease, and the total length must be equal to L. Subtracted by L, it must be equal to 0. So now we have the constraint. So now we have the constraining function. Next up, of course, we write down the we write down the kinetic energy, which is mx1 x dot squared plus 1/2 m2 y dot squared. Okay. And lastly, we write out the potential energy. In this case, it's going to be minus mgy. It shouldn't be too complicated. Yeah, okay. And so now, we write out the Lagrangian. So, Lagrangian with constraint. I'm gonna write down like this. Lagrangian I don't really know the proper term for it, but the Lagrangian constraints here is basically just saying that it's t minus L here is equal to 1/2 m1 x dot squared plus 1/2 m2 x dot squared. Why is this x dot squared? Because the rate of change of y is negative of rate of change of x. You know, if y gets longer, x gets shorter by an equal amount. And because it is squared, so the negative sign goes away. And then you subtract it by the potential energy, which is going to be equal to subtracted by m2gy plus m2gy. But y is equal to L minus x. And so there's the Lagrangian with the constraints applied to it. 1/2 m1 plus m2 x dot squared minus m2g x plus m2gl. Alright, this is the Lagrangian with the constraints applied to it. On the other hand, we write down the Lagrangian but without the constraint. Well, not really without the constraint, with the constraining force term. I think it's called the Lagrange multipliers. Yeah. The Lagrangian with Lagrange multiplier added to with the Lagrange multiplier term added to it. It's basically saying it's 1/2 m1 x dot squared plus 1/2 m2 y dot squared, and then plus m2g y. And this is the this is pretty much the same as this one, but without having the constraints applied to it just yet. And so what we got to do is we got to add the constraining term lambda f. And that lambda f is x plus y minus L. Now we don't know what lambda is just yet, but we'll soon see what it is. m1 x dot squared plus 1/2 m2 y dot squared plus m2gy plus lambda x plus y minus L. As you know, this term, you can add this term in because if x and y are according to the constraint, it's going to be 0. So if x and y are according to the constraint, this term will be 0. Now let's apply the Euler Lagrange equation. I'm not going to do the left-hand side. The right-hand side is going to be, they're going to be pretty much the same. So I'm just going to do the one on the right-hand side because it's more interesting. Half of us already know how to do the Lagrangian mechanics, right? Right? Just plug in the Euler Lagrange equation. Okay. d by dt of derivative of L with respect to x dot subtracted by L with respect to x is equal to what? D by dt of m1x double dot, no, m1x dot, sorry. And then derivative, this one becomes 0, this becomes 0, this all becomes 0. Subtracted by, we take the derivative of this one, which is just lambda x. So we take the partial derivative, it becomes just lambda. So this becomes m1 x double dot minus lambda equals 0. That is to say that x double dot equals to lambda over m. What do you think lambda is in this case? X here is the position of this guy. So lambda has what is lambda? Clearly lambda here is going to be the force. Clearly lambda here is going to be the tension force of the rope, right? Because you know, F equals ma. This is just F equals ma. Mx double dot m1 x double dot equals to lambda. Lambda, yeah. So we can claim that lambda here is just the tension force, of the rope. let's take the time derivative of the other one, of y. Whoop. We're gonna have d by dt of, I'm just gonna write m2y double dot, subtract, no, yes, okay, subtracted by m2g, yeah, m2g plus lambda. So we can say that m2y double dot minus m2g plus lambda equals 0. That is to say that m2y double dot equals to m2g plus lambda. And this is just f equals ma. On the right hand side we have f, and this is just ma. So ultimately, using the Lagrange multiplier method, by adding in the constraining term, it allows us to find the force that is constraining the system. That is consistent with the one before this. In this case, it was constraining along the theta axis. So instead of being force, it becomes a torque instead. In this case, it is constraining the length. So if it's constraining the length, the constraining force is going to be force. But if it's constraining the angle, the constraining force is going to be the torque. And so we can now conclude that basically, over here we can now write that m1 x double dot equals to lambda. In this case, it's going to be equal to t, negative t. Should I call it negative t? Yeah, because x is going down. And m2y double dot equals to m2g minus t, because again, lambda equals, because in this case, lambda equals to minus t. So, as you can see here, using the Lagrange multiplier, we get the two equations that is consistent with what we would get in Newtonian mechanics. Because this one we would have m2g, right? And so we would have y double dot equals to m2g minus t. Yeah, using the drawing the free body diagram. So here x double dot equals to negative t, which is also consistent over here. So the equations of motion here are consistent with the they're consistent with Newtonian physics, which is neat. It is really, I don't know, I just find it cool, I guess. m2y double dot equals to g minus t. In this case, it's going to be plus mx double dot then. And then y double dot is equal to minus x double dot, because as y changes, x also changes. Lagrangian mechanics will go yeah, I really like it. I don't know, Lagrangian mechanics just feels so cool. I was so excited to study it when we get to the unit in the class. When x double dot equals to m2g, therefore x double dot equals to negative m2 over m1 plus m2g, which is, we can also find this from this equation. We would also get x double dot equals to negative m2 over m1 plus m2g. We'd get the same results, but here it's a little more complicated. But we also get the tension force added for us. So that's really cool. Personally, I find really cool. We might as well also say that from here we get that the tension force is equal to minus m1 m2 over m1 plus m2g. And and as you can see, using the Lagrangian multiplier, it's really neat. Alright, so that's it for today's stream. Next week I'm planning on playing Little Nightmares on stream. Probably won't be streaming on YouTube though. I feel like when it comes to gaming, I should be streaming on Twitch. So I'm gonna be trying to stream on Twitch. I also have like a friend whom I'm gonna invite to. So like if you want to like watch me stream on Twitch, I guess you can. I haven't linked my Twitch on YouTube yet. I haven't never streamed on Twitch once, in fact. But yeah, if you want me to play games, want to see me play games, well, just be prepared, I guess. Just check back. Little Nightmares releases on the 11th. I'm not quite sure when I'm going to be streaming it. But I'll also be streaming my homework somewhat semi-consistently. When I get some more homework, I'm going to stream more of it, obviously. So, yeah. Thank you for watching. I'm going to be off to doing a little bit of testing with my computer and stuff after this. So yeah, thank you for watching. Hope you guys enjoyed and at least got some knowledge or got some practice in with Lagrangian mechanics. And I hope you guys have a nice day. See you guys. Bye.